Hello class, today we're going to describe how the distribution of speeds and average speed of gas molecules changes with temperature. We're going to describe how the relative rates of effusion and diffusion of two gases depend on molar masses, and we're going to explain the origins of the corrections to pressure and volume that occur with the van der Waal equation. This aligns well with the AP gas law free response questions, and this is the last play posit for the unit. So root mean squared velocity. This is an equation you don't see very often, but sometimes it does pop up on multiple choice. They may ask you to calculate the root mean squared velocity. It's basically the average speed of particles based on mass. So if we were to calculate the root mean square velocity of nitrogen gas and oxygen gas at 25 degrees Celsius. This is the equation that we would use. The tricky part with this is that the masses have to be in kilograms, because the R value that they use here is in joules per mole Kelvin. If we think about what a joule is, we know that it's based around a Newton, and a Newton has kilograms in as part of its unit. If you were to break down what a Newton is, we know that a joule is related to a Newton that way. So the masses here have to be in kilograms. So mass in kilograms. Otherwise, we can plug everything in. We're going to use the 8.314 version of R. So if we were to do N2, we've got the square root of 3 times 8.314 joules per mole Kelvin. Remember, your temperatures have to be converted to Kelvin, so temperature is 298 K. And then we divide by our mass of N2 in kilograms. So we know the mass of N2 is 28.02 grams per mole, right? And if we divide that by 1,000 grams, we'll get ourselves into kilograms. We know we're looking at 2.802 times 10 to the negative second kilograms. So we'll plug that in there, 2.802 times 10 to the negative second kilograms. And then we can plug that in. So I've got the square root, and I'm going to do parentheses at the top, so 3 times 8.314 times 298, close parentheses, and then divide by 2.802 e to the negative second. And I get my velocity. You can do 3 sig figs here because of our temperature value. 515 meters per second. Yes. So everything would cancel out and we would get meters per second. I won't trouble you with the units because you won't see this calculation very often. But if you were to expand out what a joule is, we would be able to figure out this is in meters per second. Okay. Now you could go through and do the same thing for O2. So go ahead and calculate O2. Okay, so for O2, if you use the same type of calculation, we know the mass of oxygen is 32 grams per mole if you're looking at O2. And if we plug that in, convert it to kilograms first and plug it in, we would get a velocity of 482 meters per second. Okay. One calculation's enough with that. Let's move on to Graham's law. So Graham's law of effusion. Graham's law of effusion and diffusion. Diffusion is the random scattering of gas molecules due to the presence of a higher concentration of gas in one area of a container than another. Essentially, it's the mixing of gases. Very similar to the idea of osmosis. We always move from high to low, or if you're thinking about energy transfer, we always move from high energy to low energy. Same deal with concentration of gases. We go from high concentration to low concentration. Different gases diffuse at different rates, and it is all based on size. If we think about this in real life, we're thinking about, say, cars on a highway. The most annoying things to drive behind are the trucks, because they're very large. And because they're very large, they move slower because it takes more energy to get them moving. Whereas the little tiny hybrid cars move a lot faster because there's less mass to deal with. So we can relate this through our kinetic energy equation. And so here's the derivation here. If you've got the kinetic energy is equal to 1/2 times the mass times the velocity squared, we can set the kinetic energy of two particles equal to each other. So you could say the kinetic energy of some first substance and then is equal to the second substance. We get 1/2 m1v1 squared equals 1/2 m2v2 squared. Those 1/2s are going to cancel out. And then what we can do is we can get velocity and mass on one side of the equation. If you divide by each other, we end up getting a velocity of the first one divided by the velocity of the second one is equal to the mass of the second one over the first one. We can relate this to a mass and rate. We can take the square root of that, and we end up getting square root of the whole thing, rather. We end up getting that the square root of the mass is equal to rate A over rate B, where the rate is a velocity in meters per second. If we were to think about the distance these things are traveling, they're traveling at the same distance when we're talking about a fusion, because the passage of the gas through the fusion is the passage of the gas through a pinhole in an evacuated chamber. So they're traveling the same distance. Since distance is the same, if we were to look at velocity, we know that velocity is distance over time. If we know our velocities, our relative velocities, and we know that our distance is not changing, that's constant, and we can also relate our time to this. So the rate of A over the rate of B is equal to the square root of the mass of B over the mass of A. And then the time is also related in that same fashion. So the rate of A is inverse to the rate of the rate of A is inverse to the time of A. So it's a very useful equation. You might see a couple of calculations with it. And let's do one. So here, calculate the ratio of the fusion rates of hydrogen gas and uranium hexafluoride, a gas used in the enrichment process to produce fuel for nuclear reactors. So we need a couple of things here. We need the masses of H2. H2, that's easy, it's 2.02 grams per mole. We need the mass of UF6, so we got to figure out our molar mass. Go to our periodic table. Let's look. We've got 238.03 for uranium, and we'll basically say 19. We'll say 19 for fluorine. So 238.03, 238.03 plus 6 times 19 for fluorine, and that gives us, I gotta put my calculator back on, that gives us a mass of, it's actually 19 times 6, and then we'll do plus 238.03. All right, 352.03 grams per mole. All right, so both of those are rather large. If I want to know the, or not both of those, sorry, UF6 is very, very large in comparison to hydrogen gas. So we expect that the rate for hydrogen gas would be a lot faster. All right. So then I want to plug in my masses, and remember it's the mass of B over the mass of A. So I've got 352.03, and this is divided by 2.02 grams per mole. All right. If I take the square root of that, all right, I get 13.2. If we were to equate that to a rate, you could then write a sentence that says H2 moves or fuses 13 times faster than UF6. Not too bad. Sometimes they might give you times. Just remember that if they give you the times and plug that in and relate that to the rate, you can skip that center step. Or sometimes they'll give you the times and ask you about the masses. We know that they're also going to be proportional given this equation. All right, so this time, try one on your own. A sample of H2 diffuses through a container 8.94 times faster than an unknown gas. What is the molar mass of the unknown gas? If we think about 8.94 times faster, treat that as a fraction. 8.94 is the top, 1 is the bottom for my rate. If we're talking about relativity, go ahead and solve. Okay, well, 8.94 over 1 is equal to the square root of x, because I'm looking for mass B, and 2.02 is my hydrogen. So I know that if I square both sides, right, I will get some value. So I got 79.9236, and that's equal to x over 2.02. Then I solve for x, so times 2.02. I've got a mass of about 162, let's say 161.44 grams per mole. Okay. On to real gases. So we've been looking at everything in this unit through the ideal gas law. We know that ideal gas behavior is not perfect. In fact, every gas does stray away from the ideal gas law to a degree, but that's why we know that ideality occurs at standard temperature and pressure. When we're talking about real gases, there is a correction that has to be made. You're not going to have to do this calculation at all, but you will be expected to know where it comes from and what kind of corrections you have to make. The key here to know with real gases is that you have to correct for volume and for the attractive forces between molecules, which leads to a change in pressure. So if we think about our original ideas of the kinetic molecular theory, we say that the volume of we assume that the volume of the gas is negligible. When we're looking at the volume overall, we're looking at the volume of the gas in the container, but we don't ever account for the volume of the particles themselves. Sure enough, if you look at something like UF6 and compare it to H2, we know it moves slower because it's much larger. If it's much larger, that does have an appreciable amount of volume in comparison to H2, so sometimes there needs to be a correction for that. So when you do that correction, you have to account for the moles and a constant, van der Waals constant, which is determined experimentally. Like I said, you wouldn't need to do this calculation, but it's good to know that the reason we're correcting for volume is because gases in real life do actually have a volume. Pressure is actually going to be a little bit higher than normal because under certain conditions, molecules have attractive forces between them when they bump into each other, and not all molecules have attractive forces between each other, but in certain conditions they can have attractive forces, and if they bump into each other the right way, right? If you think about kinetic molecular theory, and even just going back to kinetics and rate laws, if they bump into each other with the right orientation and with the right energy, they do stick together. And so with that happening, we need to correct for our pressure, because if our things are sticking together, the pressure is going to be different because we don't have as many particles hitting our container. So the ideal gas law, one of the keys here, I wrote it in green. I do want to just make sure we highlighted it. Ideal gas law is valid when we have low pressures and high temperatures. When we have the opposite, real gases apply when we have high pressure and low temp. The opposite there. Okay. So just be aware that real gases do exist, and they love giving you graphs like this, where you can see that there's a lot of deviation from the ideal gas law, and a lot of it does have to do with mass. And every gas does have an ideal pressure and temperature at which it behaves ideally, but as we get farther away, once we get up to higher pressures, we see that everything is very far off from the ideal gas law. So in this first graph, everything's at 200 Kelvin, so they're at the same temperature, but as we increase the pressure, they're going to be further and further away from ideality. So they love giving multiple choice questions about this, and you should be able to explain that, hey, they're farther away from ideality because it's high pressure and low temps, and therefore we have things like attractive forces coming into play, and we also have volume that we have to account for. The graph on the right is just for nitrogen gas. It's very clear that we have non-ideal behavior at each temperature, but the ones that are at higher temperatures have a smaller deviation. So again, high temp and low pressure is the best scenario for getting us close to the ideal gas law. And my last problem, this one is more of an ideal gas law application. I promised that I would do one of these with you. It says the density of a gas was measured at 1.5 atmospheres and 27 degrees Celsius and found to be 1.95 grams per liter. Calculate the molar mass. Well, the easy way to do this, we know molar mass is equal to density times RT over P. If you wanted to just use the ideal gas law and solve for moles first and then divide 1.95 by the moles, you could do it that way, but I think this version's easier. We've got 1.95 grams per liter. We've got 0.0821 atmospheres, liters, moles in Kelvin. Temperature 27 degrees in Kelvin would be the same as 300 Kelvin. And then we've got our pressure, 1.50 atmospheres. Okay. And we put it all together and we should be able to get our molar mass times 0.0821 times 300. And then we divide that by 1.5. And here we go. Our molar mass is about 32.02 grams per mole. If I gave you a chart and told you the molar masses of a bunch of different gases, you should be able to figure out which gas it is based on this molar mass. I think it'd be a safe bet to say that this would be oxygen gas because oxygen gas has a mass of 32, but that would be an additional extension outside of the realm of this problem. Okay. And that is all for gases. Yay, quick and easy unit. Have a great day.